Okay, so we have started looking at atomic physics from last lecture, and what we did was we said that if you take non-relativistic limit of the Schrodinger equation, so non-relativistic limit of Dirac equation coupled to electromagnetic field, then you can write down that expression, that Hamiltonian in this particular form, and of that, first two terms are the ones which are the usual Schrodinger equation for hydrogen atom problem. And in addition to that, we had other couplings which are written out here, which involves the vector potential and coupling of magnetic field to the spin of the particle and so on. Okay. So, of course, we work in A dot del dot A gauge, del dot A equals 0 gauge, and therefore we can simplify this expression. In fact, one can explicitly show that if you use the vector potential generated by, say, nuclear magnetic moment, then you could, in fact, show that del dot A is actually 0. And you can simplify this expression and write it in a simpler fashion. Okay.
Hello, sir.
Yes.
Just show me the previous slide.
Yes.
Sir, I think first term, second term, third term, and fourth term, fifth term. There are 5 terms. That sign is missing. Or plus is missing.
Yeah. Here, no? Here. Yes, I'll do that. At both places, in fact. Okay, I'll have to correct the other one also. Okay. So I'll put a plus sign here also. I'll correct that. So what I was trying to say was that you can simplify that into del dot A piece plus A dot del piece, which of course occur twice. And we will later on see that the del dot A term is not going to contribute simply because it would vanish for the case that we will be considering, namely the vector potential generated by the nuclear magnetic moment. Okay. So as I said, that the remaining terms are generated by the magnetic field generated by the nucleus, and one can kind of manipulate those terms and simplify the expression. As we mentioned last time, that in fact A0 also should be expanded in multiport expansion, but we will not really do that. Okay, so that would be the ideal thing to do, but I think those corrections are much smaller, and therefore one can ignore them to the order to which we are going to compute these quantities. Okay. So the vector potential actually has a form which is related to the nuclear magnetic moment times the gradient of 1 over r. And you can write it in this particular form by just explicitly writing out the cross product. Okay. So we want to compute del dot A for this vector potential, and you can easily check that the del dot A would vanish simply because the derivative del K del M acting on R is actually anti-symmetrized because of the epsilon tensor. Okay, and as we said last time, that these derivatives are with respect to electronic coordinates, and Mn is a function of nuclear coordinates, and therefore this derivative del K doesn't act on Mn. Okay, fine. So this is the stuff that we talked about last time. So therefore, we are essentially reduced to writing down this Hamiltonian in 3 pieces, although in fact really 2 pieces is what we would be doing, but we'll manipulate these terms one after other and bring them into simpler form. Okay, so what we have is H naught, which is the Schrodinger equation that we have already solved for hydrogen atom or hydrogen-like atom problem, and we are going to treat H1 and H2 as perturbations. Okay.
Sir,
Yes.
could we have set del dot A to be 0, say by gauge argument?
You could have done it by gauge argument also. Yes, you could have chosen the gauge, but here you can actually explicitly see that it vanishes, so you don't even have to worry about it. But yes, you work in Coulomb gauge, you'll set it to 0.
Okay.
Yeah. Fine. So we will simplify these expressions one after other. So let's look at first H1, which is A dot del piece, and we will substitute the form of A, which is coming from the nuclear magnetic moment, and that expression is given by epsilon KLM MNL times XM by R cube. This with del K acting on something on the right hand side. Okay. So this term comes because A involves gradient of 1 over R term. Okay. So it's a gradient of 1 over R term. And so if you take a derivative, 1 over R goes to 1 over R cube. And then there's a term in the numerator, because it is best to write R as square root of x squared plus y squared plus z squared. And then you can easily see if you take a derivative, it will go to the cube and not the square quantity. Okay. Dimensionally, of course, it is square because there's a 1 over R cube sitting downstairs and x sitting upstairs. So dimensionally, it is correct. Okay. Fine. So you can manipulate this expression and write down del K in terms of the momentum of operator Pk, and then you find that this expression is Xm times Pk with an epsilon L Mk sitting around here. Okay, and that tells you that this quantity is orbital angular momentum piece, and orbital angular momentum piece would carry index L, and Mn also carries index L. So this quantity is actually a dot product of magnetic moment of nucleus with the orbital angular momentum of the electron. But we know that the magnetic moment of the nucleus can be written in terms of the nuclear angular momentum I times mu times GL. So therefore, this entire expression becomes E upon mR cube times the Landé G factor times mu n times I dot L. Okay. So this is a kind of expression for H1. Okay. Let's look at H2. Okay. So this is, of course, the interaction of nuclear spin with the orbital angular momentum of the electron. Okay. This term involves the interaction with the spin angular momentum of the electron. And if we try to massage this expression, then you will see that we rewrite this expression again in the component form. There are two cross products. So first open this cross product, write epsilon K Lm Sk del L times this object with some index M. You open up that expression again and you write down three indexes, of course, M. So you assign index N to this and index P to this, and that is epsilon M N P, Mn with index N and del with index P acting on 1 over R. Okay, and now, of course, you again have two derivatives acting on 1 over R, except that L and P sit on different epsilons, and therefore this expression is non-zero. Okay, what we need to do is to use the epsilon tensor identity, namely epsilon is equal to epsilon KLM epsilon MNP is equal to delta K and delta LP minus delta KP delta LN. Okay, we will use that. We'll plug that in up here. Whenever you get delta LP, you get Laplacian. Whenever you get L and P somewhere else, then you get a double derivative acting on it. Okay. Now, of these two terms of the Laplacian acting on 1 over R would give us a delta function. So that is a term which is kind of relatively simple. Again, here we will kind of replace Mn by GL times mu n times the nuclear angular momentum, and therefore this expression is proportional up to this GL mu n times E by M factor. This expression is proportional to I dot S kind of interaction. Okay, nuclear spin with electronic spin. The term, the second term on the in the Hamiltonian, which is del L del K or active on 1 over R, what we'll do is just explicitly act this derivative on 1 over R and check what we get. Okay, so this is also something we had done last time, in fact. So when L is equal to K, you again get a delta function piece. Okay, and when L is not equal to K, then you get 3 times XL XK upon R to the 5 minus delta L K upon R cube. Okay, and what we want to do is, what we need to do is to determine this constant C. Okay, so of course this has to have a property that when L is equal to K, which will give you a Laplacian piece, which is already pulled out here. Okay, so therefore this term shouldn't be contributing Laplacian, so the term should vanish. Okay, so if you do that, then you can check that the left hand side of this expression, of course, would give you a delta function. Okay, and that quantity is, of course, as we saw, that when L is equal to K, it will give you minus 4 pi times delta function. That's the kind of normalization we use. So with respect to that, the right hand side, of course, this term would cancel out, and this term would give you a contribution which is 3 times your delta LK will be summed. So that will give you 3 times C times delta function. So if you compare those two quantities, you find that you can determine C equals minus 4 pi by 3. So we will take that factor, plug it up here, and we get del L del K acting on 1 over R to be minus 4 pi by 3 times delta LK, 3-dimensional delta function, plus this piece, okay, which looks like a quadrupolar term. Okay, fine. So again, we'll put this back into the H2 expression, use the fact that Mn is GL times mu n times I, okay, and we get terms like this. Okay, so you have multiple terms sitting around here. One term is proportional to the delta function, which was the initial one where which is this term. Okay, so you take this term and write down that as a delta function. There's a delta function contribution coming from here also. So therefore, we'll have two terms involving delta function. Which is, the second term comes from here. So the second term related to this term, which is a factor of 4 pi, has a factor of 4 pi by 3. Okay, but otherwise the rest all terms are identical. And this last piece, 3 times XL XK upon R to the 5 minus delta LK upon R cube, gives you an expression like this. Okay, remember this entire stuff is multiplied by S times Mn. Okay, so therefore, if you kind of appropriately substitute Mn to be mu L Gn times I, you get an expression like that. So of course, first two terms are kind of same form except for the factors. So you can kind of subtract that and write down 8 pi by 3 times delta function times S dot I piece, and the last piece is written as it is out here. Okay, so this is H2. So we'll combine these two expressions and write down the delta H, which is a term which involves the delta function coming from the H2, and then there are terms which involves I dot S piece coming from H2, I dot L piece coming from H1, and then there's this complicated piece sitting around, which is coming from the contribution of this expression. Okay, fine. So all these terms seem to involve delta function or 1 over R to the 5, 1 over R to the 3 kind of terms, and that they are all manifestation of the fact that we have taken nucleus to be a point particle. And this approximation would be valid as long as our assumption that the electron stays away from the nucleus. In other words, the wave function kind of is peaked away from the nucleus is correct. Okay, and that is correct, then we can continue working in this basis and compute perturbative contribution. Okay. Fine. Okay. Now, after having obtained this Hamiltonian delta H, first thing that we have to worry about is how to obtain the correction due to the delta H to the spectrum of hydrogen atom problem. And at that time, we realized that the problem that we are actually looking at is a degenerate perturbation theory problem, because every state is degenerate depending upon the J value. And if it is not the most highest J value, it is 2 times 2J plus 1 fold degenerate. For highest J value, of course, it is only 2J plus 1 fold degenerate. So if you want to compute correction due to delta H, you should be solving the degenerate perturbation theory problem. Okay, fine. So one of the things that we know from quantum mechanics 1 is that, like, whenever you encounter problem involving angular momenta and a degenerate perturbation theory, the whole game is about choosing the right kind of basis. Okay, so in the case of electronic problem, we had chosen a basis written in terms of J and Jz, and where J was L plus S. Now what we'll do is we'll write it in terms of a total angular momentum F, which is the sum of nuclear angular momentum plus the electronic angular momentum. Okay, and then instead of J and Jz, we will now work in terms of F and Fz. Okay, and instead of using this basis, which is the electronic basis tensored with nuclear basis, we'll write down a new basis, which is a combination of electronic and nuclear basis. Okay, and in fact, we will not use Mj, but we'll use the magnetic projection of the total angular momentum F. Okay, good. So in this new basis, of course, F is diagonal. So F squared acting on this gives you F into F plus 1 times the state. For being fully pedantic, I should have really written H bar squared here and H bar here, but I think I will just set H bar to be equal to 1. Okay. But if you want, I can kind of correct this equation by adding that. Okay. And Fz, of course, because this is state diagonal in this basis, Fz eigenvalue will be the magnetic projection of F for this state. Okay. Now, from quantum mechanics, we know that the new basis and the old basis are related by Clebsch-Gordon coefficients. Okay, and the Clebsch-Gordon coefficients depend upon the set of angular momenta of old basis with the set of angular momenta in the new basis. For example, old basis had L and old basis had J and I as angular momenta. The new basis has only F as the angular momentum. Okay. Now, of course, you do have J and I, but the basis which is diagonal is F and its Z component, and not J or I and their Z components. Okay. So what we'll do is basically we'll find the Clebsch-Gordon coefficient, which translates this language with Mj and Mi components to Mf components. Okay. Now, of course, the nuclear spin is fixed because we are always in the ground state, and therefore there is no way the nuclear spin is going to change. Okay, its projection may change, but the spin itself will not change. So therefore, yeah. So therefore, in the new basis, the degeneracy of the problem is coming from J and the nuclear degeneracy. Okay, these two degeneracies would be lifted when you write it in terms of this basis. Okay, so to see this, of course, we'll have to actually see how delta H acts on these states. Okay. Now, notice that like in this change of basis, there is no statement made about the orbital angular momentum term, and for a given j value, there were two different L values which were degenerate, and in the change of this basis from ji basis, ji mjmi basis to ji fmf basis, uh, there is no reference made to what is the value of L and how different values of L giving same value of J, whether they are degenerate or not. Okay, so it may seem like, that although these degeneracies are all lifted by the perturbation, L equals J plus or minus half continues to be a degenerate, continues to be the degeneracy of the problem. Okay, but in fact that is not really true. And the reason why it is not true is because the entire Hamiltonian that we have written down is parity invariant. And because it is parity invariant, it acts differently on states of different parity. Okay. And in particular, because the Hamiltonian is parity invariant, no matrix element of Hamiltonian sandwiched between states with opposite parity, even parity versus odd parity, would be non-zero. Okay, so therefore all matrix elements of the Hamiltonian which should mix L values which are differing by 1, like J plus or minus half, which are L values differing by 1, there is no matrix element of the Hamiltonian between them. So Hamiltonian knows how to segregate the different L values for a given J value simply because they belong to different parity sectors. Okay, so is this point clear? Okay, so first thing that we would notice is that like Hamiltonian will not mix the states with different parity at the first order in degenerate perturbation theory. Okay, so therefore in our leading order contribution, we need not even worry about this degeneracy because it will automatically be lifted because the action of Hamiltonian on even parity is different from action of Hamiltonian on the odd parity states. Okay, so in the new basis, okay, so because of this, even the L degeneracy would be lifted, and therefore we don't have degenerate matrix element at the end of our computation. Okay, but let's kind of go back and look at this Hamiltonian delta H. Okay, so I'm just trying to write that delta H in a compact form, but let's kind of stare at it once again. Okay, so here's the thing. There are two terms really. One term involves the delta function, delta cube R, okay, with a coupling S dot I. And then there's another term which falls off as 1 over R cube as a radial dependence. And there's a dot product of the nuclear spin with some complicated object. Okay, and this complicated vector we are going to call G. Sorry. Okay, so we're going to call that vector G. So therefore we can write down that entire expression as a delta function with S dot I and 1 over R cube with I dot G. Okay, that is our Hamiltonian. Okay, so we want to kind of find out as to how we deal with Hamiltonian of this kind. Okay, and compute the matrix element of Hamiltonian of that type. Okay, fine. Now the basis in which this Hamiltonian would be diagonal is a basis which is written out here, which is NLS equals half JLFMF. Okay, that is a new basis in which these matrix elements are going to be diagonal. But nevertheless, what we'll do is we'll continue using the old basis, which is NLSJMJ times IMI basis, okay, which is an electronic basis tensored with nuclear basis. Okay. Now, the reason why we want to do this is because some of these terms are easier to deal with in appropriate electronic versus nuclear basis instead of trying to do this computation in the fully diagonal basis. Okay, so there's something interesting to learn out here. Okay, so the first thing that we notice is that if you work in the old basis, is that the first term of the delta H is going to contribute only if the L value is 0. Okay, and the reason is that the hydrogenic problem in Schrodinger equation has a radial part of the wave function which has two kind of dependencies on the radial variable. One is the piece which falls up exponentially e to the minus some a times r, which is not important right now. But the other piece is the polynomial piece multiplying this exponential function, and this polynomial piece has a leading behavior which goes as r to the L. Okay. Now, if L, which is the orbital angular momentum, if that quantity is non-zero, then the wave function near r equals 0 would actually vanish. Okay, in fact, at r equals 0, a wave function r to the L times e to the minus r would vanish for L not equal to 0. But if L is equal to 0, then r to the 0 implies that there is no factor there. It is proportional to 1. Okay, and the wave function just falls purely as an exponential function. Okay, so the reason why only L equals 0 is going to contribute is precisely for this reason, that the wave function is non-zero at r equals 0, and delta function is non-zero at r equals 0. So only those wave functions which are non-vanishing at r equals 0 would contribute non-trivial energy for a term of this kind. Okay, any wave function which vanishes at r equals 0 would give you 0 contribution. Okay. Good. So this is the same explanation that I gave, that the radial wave function behaves as r to the L near r equals 0. Okay. Let's now look at the second term. Second term involves a dot product of something which is nuclear spin with something which is purely electronic operator. Okay. So that is the kind of expression that we have. Okay. So we have one piece acting on the nucleus of space, and another piece acting completely on the electronic subspace. Okay. So this is the reason. This is the reason why we want to work in the old basis and not in the new basis. Simply because while this term contributes at only L equals 0, this term contributes for arbitrary nuclear and electronic spin. But in this dot product, I acts on only the nuclear degrees of freedom, and G acts only on the electronic degrees of freedom. And in that sense, a tensor product state involving electronic quantum numbers tensored with state involving the nuclear quantum number seems to be the best thing to utilize. Okay. So what we'll do is we will segregate the matrix element. We write down I dot G as IK times GK upon R cube. R cube was a piece just sitting there. Here it is. Okay. So what we have is a matrix element of the kth component of the nuclear spin sandwiched between two nuclear states, IMI prime and IMI, with the appropriate factor which is there in the delta H. Okay, times the electronic part of the matrix element, which of course is written in terms of N, L, S equals half, J, MJ, times GK by R cube. Okay, so the only thing that is important here is that this entire expression is I dot K upon R cube. So it must be IK times, sorry, not I dot K, I dot G upon R cube, and therefore it should be IK times GK. Okay, that is the important aspect of it. Okay, so what we'll do is we want to solve this matrix element using the Ignorica theorem. Okay, So, what we'll do is that instead of kind of using the Ignorica theorem, we will say that this is a matrix element involving a vector-like operator. So its behavior as far as the angular momentum sector is concerned is same as any vector-like operator sandwich between these states. Okay, so of course the answer is not going to be exactly same, but it will be the contribution coming from the angular momentum sector times some number. Okay, and we want to determine what is that number. Okay, that is the exercise. Okay, so what we'll do is, instead of computing this with gk being that complicated operator L minus S plus some 3 R times R dot S upon R cube or stuff like that. Okay, what we'll do is we'll just replace this entire operator by just jk. Okay, so all we are doing is that we choose the vector operator j to replace this entire object. Okay, fine. Now, of course, the value of this matrix element is not going to be the same as the value of this matrix element, simply because the operators that are involved are quite different. Okay, but if you write down this expression in terms of Clebsch-Gordon coefficient times a reduced matrix element, then you can kind of show that, which is something which follows from the Ignorica theorem, that if you can evaluate this matrix element, then this matrix element can be written in terms of the jk matrix element times some proportionality constant. Okay, and one can determine that proportionality constant explicitly. Okay, so of course this piece contains Clebsch-Gordon coefficient, which is of course going to be common for both of them. Okay, but then there are pieces which are independent of the magnetic projections, and those are the pieces which one has to work out explicitly. Okay, and what we'll do is we will replace this vector operator by another vector operator, namely jk. Okay, compute quantities and then eventually give a relation between these two operators. Okay, so that is the exercise. Okay, first manipulate the expression, simplify, and then compute the matrix elements. Okay, is the strategy clear? Hello?
Yeah.
So main strategy basically is to say that any spherical vector sandwiched between angular momentum state is same as, has the same matrix elements as any other spherical vector. Okay, only difference would be that if that spherical vector is multiplied by something else, okay, then there may be a proportionality factor between these two spherical vector things. But angular momentum part of it, okay, you can compute by using anything which is convenient for you. Okay, so maybe you can just go ahead and see an example, not example, but see how this whole thing works out. It will probably clarify. Okay, so what we are going to do is we are going to claim that this matrix element, which is what we want to evaluate, n L s equals half j mj g k r upon r cube times n L s equals half m j mj prime is equal to some constant, which of course constant in the sense that it is independent of mj, it is independent of mj prime, is also independent of the quantum number, magnetic quantum number that gk would have. Okay, so it could only, if you take that out and you know that s is equal to half, okay, so only thing that remains here is n, l, and j. Okay, so those are the quantum numbers on which this constant k could depend. But precisely those quantum numbers are the ones which a vector operator will never change. Okay, if you sandwich a vector operator, it will change the m values, but it is not going to touch in n or l this thing. We are looking at specific matrix element involving j values to be same. So of course that also is not going to change. Okay, fine. Now of course, what is k depends upon what is g. Okay, because j is a fixed operator. Okay, as far as angular momentum is concerned, this is a vector operator and this is a vector operator. Okay, but as far as the Schrodinger equation or a hydrogen atom problem is concerned, this is operator which contains only the electronic angular momentum information, whereas this operator may contain much more information, and therefore this K not only depends on L and J, but it also depends upon what is the operator GK. Okay. Okay, so what we are going to do is, remember we had this expression where IK was dotted with GK, right? We can go back a little again. This is a term I dot G, okay? But what we are going to do is to replace G by J. That is the statement that I just wrote down, right? That because both of them are vector operators, I can just say that G upon R cube sandwich between these states is same as some constant times JK sandwich between the same set of states. Okay. So if that is a yes.
I mean, yes. I get that since G is some vector operator that is coming as I dot J in the Hamiltonian, so it seems sort of fair to call it a spherical vector. But why exactly can I call it that?
Well, because if I do a rotation transformation, then GK will transform like a vector.
This we should be able to see by G's expression, right?
Exactly. So you can see it very easily. Here it is. If you do a rotation, L gets rotated, S gets rotated, and R gets rotated, right? R dot S is a scalar quantity, R square is a scalar quantity, but under rotation, all of them get rotated. Okay, and therefore G is rotated like a vector.
Okay.
Okay. So under rotation transformation, it definitely has the same property as any other spherical vector.
Sir?
Yes.
Why is this matrix element not dependent on K? Small k.
Small k?
The index.
No, it does. It would depend on small k. Okay, so but the same small k is sitting around at both the places. The capital K won't depend on small k, okay, but the matrix elements would.
Yeah.
Okay. Yeah. So let's kind of step back a little. It may clarify some point here. Okay. See, what Ignorica theorem tells you is that if you are trying to compute a matrix element like this, then this matrix element can be decomposed into two pieces. One piece which contains information only about this magnetic quantum number Mj, K, and Mj prime. That information is sitting in the Clebsch-Gordon coefficient. Okay, once you take that information out, whatever remains, that matrix element does not have any information about the magnetic quantum numbers. It has information only about J, L, N. Okay, and had S been a free variable, then it also would have been a function of S. Okay, so Ignorica theorem tells you that the reduced matrix element has no information about the magnetic projection. Okay. So what we are doing right now is we are saying that, sorry, let me just step back again. And what we are trying to say is that this vector operator sandwich between these states, because of its kth component, has information about Mj, K, and Mj prime relation, which is a part of Clebsch-Gordon information. Barring that, whatever is the remaining information is the information which depends on what is N, L, J, and the function and the vector, the composition of the vector operator G. Okay, that quantity is independent of the magnetic projection, and that quantity would be the same as the quantity here up to a factor. Okay, which is related to choice of this function, which is what we call capital K. Okay, so this is the Clebsch-Gordon piece, and this is the reduced matrix element. Okay, that is how we are using Ignorica right now. Okay, so now what we will do is we'll actually replace this complicated matrix element by just K times the same kind of matrix element, but of J. So if you do that, then you replace this matrix element that we want to compute by the matrix element, which is K times I dot J, because G upon R cube is same as J, up to whatever that complicated object K is. Okay, we will determine K eventually. Okay, but right now, the spherical tensor property tells you that you can replace I dot G by I dot J. Okay, notice that the states are exactly same. N, L, S equals half J, I, F, M, F, which is the same state written here. N, L, S equals half J, I, F, M, F prime, which is the same state written out here. Okay, so states are not changed. Operators have been traded off by saying that you use this. Okay, now the thing is that, like, although the basis that we have used here is the new basis, like I explained some time ago, if you have an expression which is written in terms of I dot J, for example, it is easiest to work in the old basis, because I would kind of talk to the nuclear spin and J would talk to the electronic spin. Okay, so one could actually compute this in the old basis, and then when you want to write down the result in terms of new basis, you of course have to take the Clebsch-Gordon coefficient into account. Okay, you need to insert the Clebsch-Gordon coefficient and some overall combinations which would give you the states in the new basis. Okay, fine. Now remember that, like, as I said, and as Harshit also asked a moment ago, this thing that these matrix elements are really Clebsch-Gordon like matrix element. Okay, whereas K is independent of magnetic projection, so therefore you can just pull it out of this matrix element and write it outside, which is what we have done in both these expressions. Okay, so eventually if you find that the K is a function of MF, then this entire computation is wrong. Okay, this entire stuff is based on the Ignorica theorem, telling you that K is part of the reduced matrix element, doesn't know about magnetic projections at all. Okay, fine. So now what we'll do is we'll replace I dot J by using the same old trick that we did in quantum mechanics, where we replaced L dot S by J squared minus L squared minus S squared. We'll do the same thing here. We write I plus J is equal to F, and then write down I dot J is equal to F squared minus I squared minus J squared by 2. Okay. Of course, if you use this basis, then of course the new basis is most convenient, because that is the basis in which F squared is diagonal, and you can compute the eigenvalue of this matrix element. Okay, so let's do that. Take the new basis, substitute I dot J by this quantity. Okay, and just compute its eigenvalue. Okay, this expression would be non-zero simply only when MF is equal to MF prime, simply because F squared, I squared, and J squared are diagonal. They have eigenvalues with respect to this state, and then orthogonality of these states tell you that unless MF is equal to MF prime, this matrix element is just going to vanish. But when the matrix element does not vanish, namely when MF is equal to MF prime, you know what this what is the value of this matrix element, namely half times F into F plus 1 minus I into I plus 1 minus J into J plus 1. Okay, is that fine? Okay, I suppose this is okay. So what we'll do is we'll take this and plug it back into our relation. Our relation was this. All we have done is computed I dot J. So this matrix element is K times whatever we have just computed. Okay. So let's do that. Okay. Now, the fact that delta MF prime is the only case where you get this non-zero answer can also be seen by this kind of argument, in that I dot J is a scalar operator, and scalar operators cannot change the magnetic projection. Okay, that is yet another way of looking at it. There are four or five different ways of explaining the same stuff. Okay, so So what we have done is we have determined I dot G in terms of I dot J, okay, because we know exactly what is its dependence on total angular momentum, nuclear, and the electronic angular momentum. Only thing that we have not done so far is determining what is K. Okay. Now, once you determine K, then our job is done, because you can take that thing, plug it back into the Hamiltonian, and find out what is the expression for delta H. Okay. We know how it would act on a particular angular momentum state. Okay. Fine. Now, as I said some time ago, that K is independent of the magnetic quantum number, and therefore it must be a function of the reduced matrix element. So there is some operator sandwiched between this double barred Ket-Brahe states, okay, and K must be function only of this and not of these quantities. Okay. So question is, how do we determine it? Okay. So let's do this computation. So to do that, okay, remember what we have done so far is that we had an expression. Okay, let me step back a little. We had an expression which was I dot G. Okay, and we said that, like, instead of computing I dot G, let's compute I dot J. Okay, and then we said that, like, once we compute I dot J and once we determine what is K, then we have determined what is I dot G. Okay. Now, to determine K, what we will do is, K is of course related to the matrix element of G upon R cube. But what we will do is that instead of looking at that expression, we start off with some other starting point. Okay. Namely, we look at the term which is G dot J. Okay. So here's the term. So we start with the matrix element sandwiched between the same states. Notice this difference. That was MJ, MF, MF prime kind of stuff. We are working exclusively in the electronic basis now, okay, which is the original electronic basis and not the new basis involving F, MF. But we are working in this old electronic basis, and we are computing a diagonal matrix element, MJ, MJ on both sides, and we are looking at G dot J upon R cube. So MJ, MJ is chosen simply because we have already learned that if you have a scalar operator sandwiched between the states, then the magnetic quantum number doesn't change. Okay, so this is the only non-trivial matrix element that we would get, but we want to compute this now. Okay. Now what we'll do is we'll insert complete set of states between GK and JK. Okay, so this is what is the stuff. Okay, so we are going to sum over all kinds of states which are sandwiched between GK upon R cube and JK. Okay, and we want to compute these matrix elements. Okay, fine. Now, GK is of course operator of this kind. We have seen it earlier. Okay, so this matrix element could in fact change the value of MJ. Okay, and the change in the value of MJ could occur because of any of these operators. Okay, so prima facie it looks like which one is changing, whether this guy kind of changing or whether RK is changing and so on. Looks like a complicated thing to determine. Okay, so what we will do is we will first look at the matrix element involving JK. Okay, and then we can come back to GK upon R cube matrix element. Okay, so JK matrix element is kind of easy. Okay, so since JK is a vector, okay, it would act. Oops, there should have been a space there. Okay, it would act on a state. So let me just kind of show you here. Since JK is a vector operator, it can change MJ value by plus or minus 1, or can keep it as it is. Okay, so therefore the state alpha that for which JK would have non-vanishing matrix element would have a MJ prime value, with MJ prime is equal to MJ plus or minus 1 or MJ. Okay, that depends upon what is the value of K. Okay, whether K is 1 or K is minus 1 or K is 0. Okay, would determine which one of these are going to click. Okay, but But Jk being a vector operator has already determined which alpha states here are going to give you a non-zero matrix element on this side. Now this state has to be same alpha simply because you are kind of substituting a decomposition of identity. So therefore, once you know this alpha, you know this alpha. Okay, then all you need to check is that with respect to the alpha for which Jk has a non-trivial matrix element, for that alpha is this matrix element non-zero. Okay, so that is the exercise that we will do. Okay, so does this sound okay? So what is going to happen is that the matrix element is going to look like this, that the sum over alpha basically corresponds to the same states with same quantum number n, l, s equals half j, only mj value can change. Okay, so sum over alpha just corresponds to sum over all possible mj prime values, and our matrix element therefore is reduced to computing these two matrix elements. Okay, is this okay? Am I going too fast?
Okay, sir. Okay.
Okay. Okay. So what we want to do is to figure out how we compute this product of matrix elements. Okay. And what we are going to do is that we are going to use the same trick that we used some time ago. Namely, we would replace gk upon r cube, which is by another vector operator. Because after all, this is a spherical vector. Okay. We write that in terms of another vector times some proportionality constant. Which one we want to use? Well, we'll use the same one that we used some time ago. Namely, we replace gk upon r cube by k times jk. It is the same k that we used some time ago, right? We said that we are going to replace gk upon r cube by k times jk. Okay, so which is the same thing that we'll do again. So we replace gk upon r cube by k times jk. Once you do that, then you get your matrix element to be k times sum over mj prime with the states completely copied from the top. Okay, only difference is gk upon r cube is replaced by jk. Okay, now notice one important thing here, that this summation is a decomposition of identity. That means this all allowed states here and these states here actually sum up to give you identity. So therefore you can just get rid of this summation and remove this and replace that by an identity element. Okay, but if you do that, then what you have is this brass state times jk times jk times this ket state. But jk times jk is just j squared. Okay, so therefore our matrix element is just k times the matrix element of j squared, sandwiched between the same states. Okay, and that we know, of course, how to compute. That is just j into j plus 1. Okay, so the matrix element m, which is g dot j, that is what we started off with, is just k times j into j plus 1. And therefore, k is m gj upon j into j plus 1, which is same as 1 over j into j plus 1 times this matrix element. Okay, because m gj was precisely this matrix element. Okay, I have not written s equals half because that was kind of overshooting into the page, but this state and this state is really the same. Okay, so what we have found out so far is that k can be written in this particular form. And from this expression, it is clear that k is independent of the magnetic quantum numbers. Okay, it doesn't look like that right now, but g dot j is a scalar operator, and therefore it is independent of magnetic quantum numbers. Okay, and therefore we know that j is independent of magnetic quantum numbers. Okay, but although we have obtained k in this particular form, we actually haven't obtained derived the expression for k explicitly. All we have done is we have traded it off to another matrix element which needs to be determined. Okay, up to only improvement that we have done so far is that that matrix element is multiplied by 1 over j into j plus 1. Okay, that is what k is. Okay, so the exercise that we need to do is to determine this quantity. Okay, are you with me on this? Okay, so maybe I can go ahead. Now recall that the operator G had this expression. Okay, same expression we have kind of written it down several times. Okay, so here's the form once again. Okay, so what we will do is we will take this operator and plug it into this dot product. Okay, and compute that quantity. Now, before we compute that quantity, we need to do one more thing, that G is given by this operator form, but we also know what is J. J is L plus S. Okay, so we are going to write down G dotted with L plus S. Okay, so that expression is kind of easy, because if you take that product, then G dot J would give you L minus S dotted with L plus S. That gives you L squared minus S squared. And then there's a L plus S dotted with this object. Okay. If you take that dot product, then what you'll get is 3 upon R squared times S dotted with R squared. Okay. Is that fine? And that is, you don't get a L dependent piece simply because L dotted with R is equal to 0. Okay. Is that fine?
Yeah.
Okay. So because of that, G dot J can be written into as L squared minus S squared times 3 upon R squared times R dot S. Okay, whole squared. Okay, and there is no L dot R piece simply because that is just 0. Okay, fine. Now remember that so far we are still considering a single electron problem, so there is some additional simplification that we can utilize here, and that is that the system that we are considering is a spin half system. Okay, and because it is a spin half system, we can replace S by the Pauli matrices. Okay, so S operator can be written as half times the Pauli matrix. Okay, so therefore you can write down R dot S as half of R dot sigma. Okay, but R dot sigma is something you can compute. R dot sigma square is just, R dot S squared, I should have said. R dot S squared is equal to 1/4 times R dot sigma squared. And you can compute this quantity, that will just give you R squared. Okay. When you take this product, you get sigma I times sigma j, which gives you delta ij plus I epsilon ijk sigma k. But that epsilon ijk term would give you a 0 answer, because epsilon ijk is antisymmetric in ijk, but that will be multiplied by ri rj, which is symmetric in ij. Okay, so only this term would survive. Okay, so this should have been R dot S squared piece. Okay, so what we'll do is we'll substitute this quantity up there, and you can see that the R squared will cancel out, and you get the answer which is 3/4. Okay, so what you get is the expression like this, that G dot J is L squared minus S squared plus 3/4. But remember that we have used the fact that we are working with single electron problem, and that is a spin half system. Then you might as well use the spin half system here also. And then if S is equal to half, then S squared is 3/4, because S into S plus 1 is 3/4, and that just cancels this factor. Okay, and what you get is G dot J is just L squared. Okay, is that fine? So there's a series of manipulations to just simplify the expression. Is this okay? Am I going too fast?
No, it's fine.
It's fine. Okay. So what we get is basically the matrix element of L squared, but that is a good object, because remember G dot J is sandwiched between states of this kind. Okay, but states of this kind are not good states if you want to look at the magnetic projection of the orbital angular momentum. But if you are looking at only L squared, then these are eigenstates of L squared. Okay, they are not ML eigenstates. Okay, but we don't need ML at all because our operator eventually is just L squared. Okay, fine. So what we'll do is we'll just take this, substitute it in the matrix element for K, which is the stuff that we are looking at. Okay, K is written as 1 over j into j plus 1 times this object. Replace this quantity by L squared upon R cube inside this matrix element. Okay, fine. Now notice one thing, we are carrying the R cube with us. Okay, there is a principal quantum number sitting around here. This matrix element contains the radial part of the wave function. Okay, and we are not kind of, going to abandon that piece. Okay, we need that and we'll compute it. Okay, but as of now, we are still manipulating the spherical tensors, spherical vectors really, and we'll compute those quantities first, then worry about the radial part of the problem. Okay, good. So let's substitute that. If you do that substitution, then you get, okay, sorry, maybe I should say one thing, that when you substitute g dot j is equal to L squared here, okay, then you notice one important thing, that you don't need to compute the radial part of the wave function for L is equal to 0, because when L is equal to 0, L squared acting on this state will give you 0. So K just vanishes for L is equal to 0 state. Okay. So only non-vanishing contribution that this matrix element would give is when these states that we are looking at are have L value not equal to 0. Okay. Now it is interesting for the following reason, that if you go back to the Hamiltonian that we are looking at, lots of steps behind. So here's Hamiltonian. It contained two pieces. One piece was the delta function piece, and another piece is I dot G piece, which is the one which we are manipulating right now. Okay. This delta function piece gave you answer 0 whenever L was not equal to 0. Okay, because L not equal to 0 corresponds to those radial wave function which vanish at R equals 0, and this term is non-zero only when R is equal to 0. So therefore, this would not have contributed when L is not equal to 0. In this expression, we found that if L is equal to 0, then this term is not going to contribute. Okay. So in delta H, we have two different contributions. First term contributes when L is equal to 0. Second term contributes when L is not equal to 0. Okay, so in some sense, we managed to segregate the orbital angular momentum part of the story. Okay, good. So let's ask, what is the value of K? Very slow scrolling, but I will reach there eventually. Okay, so here's a statement that when L is equal to 0, K would just vanish. And when L is not equal to 0, then the eigenvalue is just L into L plus 1 upon, of course, J into J plus 1, which was the factor we had pulled out earlier. And then you have to compute the matrix element of 1 over R cube. Okay, so we have figured out one more term for describing K. First step was to determine that the denominator was J into J plus 1. Now we have figured out that the numerator angular momentum part is L into L plus 1. Okay, what we want to do is to figure out what is this matrix element. Okay, fine. So now to determine this matrix element, we really have to just compute this quantity. Okay, so to do that, let's go back to the radial wave functions of the Schrodinger problem. Okay, and compute this expectation value of 1 over R cube in these states. Okay. Now remember, in this computation, L S, J, Mj are not really relevant. Okay, well, L is relevant, but S, J, Mj is not relevant. Only thing that matters is N and L. Okay, and therefore R carries that information, R and L. Okay, and here is the expectation value of 1 over R cube. The term in the denominator is just ensuring that R and L is the normalized wave function. Okay, so d cube R, of course, is written as 4 pi R squared dr. Okay, so if you do that, then you get a term which is 1 over R piece. Okay, he's talking with you. So it gives you a 1 over R term times R in L mod square. Denominator, of course, has R squared dr times R in L mod square. Okay, so this is a computation that one has to, of course, do it explicitly. For the radial part of the wave function, we know exact form of R in L when we solve the Schrodinger equation. For any given value of N and L, we know how this is going to behave. So we need to just compute this matrix element. Okay, I'm going to use a shorthand notation for this expression, which is just the expectation value of 1 over R cube, and that quantity explicit computation gives you expression which is like this. Okay, it gives you Z e squared m whole cube upon the principal quantum number cube times L into L plus 1 times L plus half. Okay, that is the answer of this particular computation. Okay, I mean, it's not very difficult computation, but algebraically it will just look complicated if I write down this whole thing explicitly. Okay, but yeah, it's quite doable. Fine. Now, this expression, a lot of terms can be explained quite easily. Remember, this term is proportional to 1 over R cube, so this quantity has length dimension 1 of 1 over length cube. Okay, that is what this means. Okay, and that explains why you get Z e squared m cube here, because the Bohr radius is proportional to 1 over Z e squared m. Okay, so this quantity is basically proportional to the third power of the inverse Bohr radius, and that's why you have Z e squared m cube sitting in the numerator. Okay, other pieces are of course dimensionless, and to get those right, you actually need to do this computation. Okay, so only thing that we could have safely determined would have been this factor. Proportionality requires explicit computation. Okay, fine. So take this and plug it back into the expression for K. We have computed this matrix element. Okay, put it in, and you notice that the L into L plus 1 in the numerator gets cancelled by the L into L plus 1 in the denominator here, and you get K to be Z e squared m cube upon n cube times J into J plus 1 times L plus half. Okay, so are you with me on this? Hello?
Yeah.
Yeah, okay. So what we'll do is we'll take this and put it back into our original proposal. Original proposal was replace I dot G by I dot J, right? So we can write down that matrix element back again, okay, and write down the contribution, okay, using these factors. Okay, so remember, yeah, maybe I should probably split the screen. Just a sec. Yeah. So here's the expression. So what we are going to do is basically write down the energy correction in terms of the parameters that we get. Okay. So right now we are just looking at the second piece, and second piece we had figured out that it was written as f into f plus 1 minus I into I plus 1 minus j into j plus 1 times some coefficient k, and that we have determined here. So we substitute this coefficient k here. Then there is a original Hamiltonian had E upon m gl mu n factor sitting around. Okay, so all those factors are written. This factor of half because I dot j is written as half of all these quantities. So that's why this factor of 2, and everything else is kind of following up here. Okay, fine. Now, this is a contribution that we obtained from the expression that we got for k, which is non-zero only when L is not equal to 0. Okay. For L is equal to 0, of course, we have this expression, and this expression is actually rewritten here: 8 pi by 3 times E by m times mu L Gn times I dot S times delta function expectation value that we need to compute. Okay. Fine. So what we'll do is, we are working with L is equal to 0, and our J is L plus S. And for L is equal to 0, L plus S is same as J. Okay, because if L is equal to 0, this operator is not important, and therefore you can replace I dot S by I dot J as long as you know that you are working with L is equal to 0. Okay, and that you are working with L is equal to 0 is not something you need to enforce here, because that is naturally enforced by the delta function. That only L equals 0 case that the radial part of the wave function is going to click. Okay, so therefore you can happily replace S by J. And once you write down this expression as I dot J, then you know what to do. Namely, you replace that by half f squared minus I squared, or is a bracket closing, I forgot, f squared minus I squared minus j squared, and plug in the eigenvalues of that. Okay, which is kind of straightforward thing to do now, right? The eigenvalues are half of f into f plus 1 minus I into I plus 1 minus j into j plus 1 multiplied by 8 pi by 3 times E by m times GL times mu n times the expectation value of the delta function in the radial wave functions. Okay. So when we compute that quantity, we need to compute this. Okay. So here basically, again, same notation that I'm using, that the expectation value of this is expectation value not in the vacuum state, but in a specific hydrogen atom state with principal quantum number n and orbital quantum number L. Okay, fine. Now, when you want to do this computation, then first thing, as I said, is that this computation is going to click only when L is equal to 0. Okay, otherwise it's not going to work. Okay, so therefore what we want to compute is to set L is equal to 0. Okay, and I shall set L equals 0 in the denominator also. But so first thing you do is you set L is equal to 0. Once you do L is equal to 0, then the delta function enforces that the numerator integration, okay, just gives you the value of the radial wave function at r equals 0. Because when you do this integration, delta function basically would tell you whatever is the value of the remaining function at the point at which delta function is non-zero. Okay, so therefore what you get is this quantity to be the mod square of Rn0, okay, at r equals 0 divided by the normalization of the wave function. Okay, so I shall release an Rn0 here. Okay, now that is not a very difficult thing to do. Normalizations of these wave functions have been known. You can open any quantum mechanics book to find what the answer is. Okay, and put that back in, and you get the answer, which is ZE squared m cube upon pi times n cube. Okay, that is the answer. Okay, now again here also the fact that you get the third power of inverse Bohr radius sitting around here completely owes its origin to the fact that you're looking at the third power of delta function. Okay. Now, delta cube has dimension of 1 over length cube. And that is the reason why this factor is sitting around in the numerator. Okay. And to see why the delta function has dimension of 1 over length cube, you do the following thing. You use the delta function identity delta a times r is equal to 1 over a times delta r. Okay. So that tells you that if you change the length scale from r to a times r, then delta function goes to 1 over a times delta function. Okay. Clearly, that implies that delta function must be having dimension of 1 over length. Otherwise, you wouldn't get 1 over a in the expression. So third power of delta function clearly tells you that the third power of inverse Bohr radius should be sitting around here. Okay. So good. So what we'll do is we will use this fact and take this expression and put it back into the expression for delta H. Okay. So further massaging is required, but I'll stop at this point and we will put all those factors together, the contribution of delta function piece and a contribution of 1 over r cube piece to write down the delta E, but that I'll do in the next class.
So what you have written about could you scroll up?
Sorry?
Could you scroll up the delta E?
Scroll up, yeah. Here?
This you have explicitly written for L not equal 0, you're saying?
Yes. I should have written delta H2 actually. I should have written only H2. Correction due to H2 is this.
Yeah, that is fine. If you could go back above, we were arguing that for L equals 0,
yeah,
that K is 0.
Yes.
I mean, that is coming from that L square does not act on the L equals 0 state, and that will give us 0. But even the rest of the term diverges, the 1 by r cube term, because it has a 1 by LL plus 1. Like when we are computing 1 by r cube over all states.
That is right. But those two are independent computations, right? You look at the angular momentum factor, okay? And I understand what you're saying. That this L into L plus 1 actually cancels out here.
Yeah, okay. And for L equals 0, we should sort of explicitly write it down in the operator form, in functional form, and complete the integral. And that will give a finite answer.
No, it doesn't give you a finite answer. It will give you a vanishing answer, in fact. If you do a full computation using the whole hydrogen atom basis, you'll get a vanishing answer for this.
I mean, okay, I have to see that. And also, why are we using the Schrodinger functions? Why can't we simply, we did find out exact solutions, right?
You mean the radial functions? They're same, even for Dirac
case, yeah.
Even in the Dirac case, they're the same wave functions.
I mean, the N and L change by some L prime and all, right?
That is right, yeah.
So shouldn't we be using those?
No, because we are actually solving the non-relativistic problem. No, in atomic physics, the energy scales involved are such that electron is still in the non-relativistic state. The kinetic energy of electron is much lower than its rest mass. So that is why we in the last class said that we will solve the H0 problem exactly and treat H1 and H2 perturbatively. H1 and H2 are contributions coming from the Dirac equation, but in the non-relativistic limit, their contributions are much smaller. Okay, they give small splittings compared to the original hydrogen atoms spectrum.
Okay.
So that is the reason why one is doing this. So of course, if you try to kind of look at something like cesium atom, which has like very high Z value, and go to a state where you kind of strip off all the electrons and keep only one electron, that electron in its ground state may have energy kind of proportional to the rest mass of the electron. Okay, something of the order of like 200 keV or something. But still, if the total energy is 200 keV and rest mass is like 500 keV, it's a good approximation to treat that electron also as non-relativistic. Okay. And cesium is like heaviest non-decaying or non-radioactive kind of what is it called, alkali atom available. So even in those cases, the electron in the lowest possible state would be non-relativistic actually.
Okay. Also, another thing I wanted to ask, like for electron, through Dirac equation, we sort of see that the gyromagnetic ratio comes out to be 2.
Yeah.
And we can form such orbital systems for higher spin objects also, right? Mesons and all.
That is right. Yeah.
At least in principle. So for those also, we should be able to write in principle a gyromagnetic ratio.
Yes. Yes. So if you construct, say, a pionic atom, you can write down the gyromagnetic ratio. It turns out to be 1.
For mesons?
For pions. Yeah.
Pions. Okay.
Yeah. Yeah. The other mesons are so short-lived, you cannot even create a state of that kind. But pion, you can still hope to do. It has a kind of microsecond life. Kaons and all are like nanosecond life. It's really hard to kind of construct. By the time it completes an orbit.
Experimentally, it might be tough, but this information is encoded in the equation itself, right?
Oh, yeah. Theoretically, you can compute, but you want to check experimentally, and you can do this with pion. In fact, you can do even muonic atoms. Replace electron by muon. Okay, and even in those cases, you can check that the muon gyromagnetic ratio is 2. So it is it belongs to the category of fermion with kind of spin angular momentum, as against pion, which is like a boson with no spin angular momentum. Okay. And the reason I said pion is because it is relatively long-lived. It's the lightest meson and therefore long-lived, whereas kaons or other mesons which are heavy and they are like much shorter-lived. Many of the mesons, the heavier mesons, are decaying because of strong interaction, and the strong decay guys, like their lifetime is less than kind of picosecond. But even kaons have a lifetime which is of the order of nanosecond. By the time it kind of would make one orbit, it would have probably died. Okay, so that is the reason why pionic atoms have been attempted. But like maybe the technology is good enough to do it with other next level mesons also. I don't know about that.
Yeah, I was trying to ask, like, for different representations, we have a different equation, right, for the particle?
Yes.
Like for spin half, we have the Dirac equation.
Yes, spin 0 is Klein-Gordon.
Yeah, spin 1, spin 3/2, and so on. We can sort of write them all. And in each of these equations, we should be able to like write down what the gyromagnetic ratio is. Yeah,
not write down. You derive it from there.
Yeah.
Okay. In Dirac case also, we did not put it in by hand. It came out as an output, right?
Yeah. So
you do get it.
Like we also somewhere say that if we have 2 spin half particles in some bound state or something, we can sort of treat them as a spin 1 particle.
Well, it depends upon what is the state in which it is, no? The 2 spin half particles can be in the spin 0 state, which is like a meson, or it can scalar meson, or it can be in a spin 1 state, which is like a vector meson. Yes, indeed.
Yeah. So in the spin 1 state,
like
similar to how even though proton is not a fundamental particle, we can perhaps treat it as a spin half particle for the calculations.
Like that we can treat these as vector mesons. Absolutely.
Yeah. So like won't the gyromagnetic ratio be different regarding, like, if it's a single electron, then it's coming out to be 2, but if we have a bunch of electrons, then it's coming out to be something else. So it does happen like that. It's like, for bound state, definitions of these kind are quite complicated actually. And, it is not so easy to kind of define what this gyromagnetic ratio would be or what the spin would be. So, for example, if you ask what, I'm jumping ahead into particle physics course, but we know that protons are made up of 3 quarks. Okay, and every quark has spin half.
So you would think that like, the vector addition of three spin half objects can be either a spin half object or spin 3 half object. Okay, so proton is spin half object, so you know as to how you construct the spin half state out of 3 spin half particles. Okay. Now you do an experiment and ask, what is the percentage contribution of these 3 quarks to the spin of the proton. Okay, and this answer in fact depends upon energy scale at which you may do the measurement. Okay, so as a function of energy is exactly the way I was saying in that I think in the advanced StatMech course, that the coupling constant is a function of energy. That electromagnetism coupling constant is 1/137 at atomic energy scale, whereas it is like 1/129 at very high, like about TeV scale. Like that, the contribution to proton spin is a function of energy at which you probe the proton, and if you probe the proton at about 100 GeV, then the total contribution of these 3 quarks to protonic spin is about 12%. Remaining 88% comes from all other particles sitting around inside the proton. So bound states can be a very complicated object, and you cannot really say that that the gyromagnetic ratio of a bound particle is just simple sum of the gyromagnetic ratios of individual objects. Actually, it is not. So proton spin was a puzzle for quite some time. It took about a decade for people to understand exactly how you really understand this stuff. And this story is not very old. Proton spin problem was discovered in around 1988, 89 or something. And just around the turn of the century, people got a good picture as to, I wouldn't say that the problem is completely solved, but at least they have understood as to why it is like this. Why only quark contributing 12% and gluons and sea of quark antiquark pairs contributing 88%. Some understanding is there now, at least. So bound state is a tricky issue, certainly.
Yeah. Also, last time I asked you something regarding the nonlinear transformations.
Yeah, sorry, I didn't get time to think about it actually.
Yeah.
Yeah, sorry, I'll look at Peskin-Schroeder at some point and get back to you.
Okay.
I'm sorry, I just didn't get time. Any other question?